Okay, welcome. So we're going to talk about kinetic molecular theory right now. So that's where the K, M, and T come from in that abbreviation. So kinetic molecular theory. Um, I just want to. I know you read about this. I just want to comment on a few things real quick, and just kind of point out some things that I'll bet you already knew as you read through the postulates. So the first statement is that particles are so small compared with the distances between them that the volume of the individual particles can be assumed to be negligible or zero. Okay, so really the main thing is just remember toward the beginning of the year when we contrasted the three states of matter and the big difference between gases versus liquids and solids is that gases, the particles are not close to each other, right? There's a lot of space between the particles. So that's really all this first postulate is claiming. So this is really something that you know, been there, done that. You kind of knew that. Number two, it says particles are in constant motion. Okay, you know, I'm sure you kind of suspected that. But the second sentence of this postulate is really, really important, and it's what connects the, you know, the I guess the experience of pressure. You know, when you measure gas pressure on the macro scale, uh, what's causing the pressure are the collisions of the particles with the walls of the container. Okay, so this is sort of this is the bridge between the molecular level and the human scale. It's the kind of um, rationalizes our experience of gas pressure in terms of molecular scale events. Okay, so that's really, really important. Okay, so number three, the particles are assumed to exert no forces on each other. This one, just take it on, just kind of accept that for now. It doesn't really have any major impact on what we're trying to do right now. But number four, this one, again, I hope this felt familiar when you read it. When we talked about temperature back in the first thermochem unit, you guys, defined it and said that it was a measure of the average kinetic energy of the gas particles. So hopefully number four felt very familiar to you. So that's great. All right, now this table, hopefully you guys were able to open this on Google Classroom, and I want you to, what you're going to do is for each row, this, moles and volume and temperature, you're going to circle one of these choices. You have three choices under the collision force column and under the collision frequency column. So the force we're talking about the force of the collision between a gas particle and the container. Frequency means like how quickly are these collisions happening. Okay, so all right, so let's try the first one, and we're going to use I've got a simulation here that I'm going to use to kind of help us um, figure out how to respond to this table. All right, so the first row here, what it's saying is basically as the number of particles in the gas, our sample of gas, increases. So the upward arrow means we're increasing the amount of particles. Lowercase n stands for moles, which is kind of the same thing. And so the first question we're going to grapple with here is what happens? What do you think happens to the average force of the collisions with the walls of a container if we simply add more particles to a container while keeping the temperature and the volume constant? All right, well, let's go down and we're not going to be able to see this directly, but I think you'll get an intuition for it. Okay, so right now we have, as you can see down here, 50 particles in the chamber. We're at a temperature of 300 Kelvin. All right, so again, that's like a nice spring day. The pressure inside is 5.8 atmospheres. And the width of our container is now 10 nanometers exactly. And so all we're going to do is we're just going to like put some more particles in there. Um, and you know what? I shouldn't have done that. Let me back up. I got ahead of myself. Okay, so back to 50. Now we're going to use this wall collision counter, and we want to get a feel for how many collisions are occurring in a given period of time. So the sample period is 10 picoseconds. So that was about 88. Okay, I'm going to run it again. Let's see how many collisions we have this time. 103. All right, now there's going to be some variability here. Okay, 96 that time. So I'll run it a few times. So with 50 particles in our chamber, you can get a feel for how many collisions are occurring in a 10 picosecond time period. So it's somewhere between 90 and 110, something like that. Okay, so just kind of remember that. Now I'm going to add another 50 particles. So we're doubling the number of particles. Um, and I think you can probably guess what's going to happen to our collision frequency here. Let's see how many collisions occur now. Oh, 182. All right, let's try it again. Oh my gosh, 202. So I think it's safe to say, let's go back. I think it's safe to say that as you increase the number of particles in your sample, keeping temperature and volume constant, that the collision frequency increases. There's no doubt about that. But what about the force of collision? All right, so let me go back here. Let me get my benchmark. Okay, so I just put 50 particles in here again. We're at a temperature of 300. Now let me add another. I've just again doubled the number of particles. And what has happened to our temperature? Nothing. In fact, let me put another 50 in here. And do you see how the temperature is just kind of holding steady? And so if the temperature remains constant, then that means that the average kinetic energy of the particles is constant. And so therefore the average force of collision, the collision force is not changed by the simply adding the number of particles. Okay, so that's that. All right, now let's go on to volume. Let's go back. So we're going to take the volume and we're going to increase the volume. Let me get the width measurement here. Okay, so this is going to be 5. I'll get it, as close as I can. All right, particles. I'm going to put 50 in here. And let's get the collision counter going. All right. All right, let's measure some collisions. 123. All right, let's try it again. 134. All right, you get the picture. 124. Okay. Now, we are going to keep the temperature constant, and we're going to simply increase the volume from 5 to 10. All right, there we go. All right, so see how everything is the same. All we did was we just simply opened up the space for the particles to roam around in. Now, what do you think is going to happen to the collisions? Okay, 98. Remember, they were like in the 120s, 130s. So we are not getting anywhere close to 100 this time, right? So the collision frequency has gone way down. And the reason for that is because these particles have a much longer way to go between collisions with the walls. And so since they have a longer distance to travel, it's going to take them a little bit longer. And so they will hit the walls less frequently. All right, so when we increase the volume, the collision frequency definitely decreases. And that happened with no change. That does not affect the average collision force. Okay. All right. Now, finally, um, we're going to see what effect does temperature, increasing the temperature, have while keeping the volume constant. All right. So let's just do a reset. And again, 50 particles. Okay. Collision counter. Now we sort of have a baseline for this, right? We sort of counted this before. All right, 84. I'll just do it twice. I'll do two trials. So we had 84. Oh, wow, two 84s. All right, now we're going to, what's the thing say? We need to increase the temperature. All right, so what's that going to do? If I double the temperature, let's try to get it as close as we can to 600. All right, close enough. All right, now do you see what happened to the speed of the particles? They're definitely moving around faster. So they're going to cover the distance between the walls much more quickly. It's going to take less time. And I'm guessing that the collision rate is going to go up. And indeed, it does. Okay, so we're consistently over 100. And not only does the collision frequency go up, but what do you think increasing the temperature is going to do to the force of the collisions? Yes, it's going to increase the average kinetic energy, and therefore the speed is going to go up. All right, so what do we got? Collision force increases and frequency increases. Okay, so to summarize, when you increase the number of particles, and that's all you do, it does not change the collision force of the particles, but it does increase the collision frequency. If you increase the volume and provide more space for the particles to roam around, that also does nothing to the collision force, but it will decrease the collision frequency. So there's kind of an inverse relationship here between volume and collision frequency. And when you increase temperature, it's like a 2-for-1 special. You increase both the force and the frequency. Okay, so that's really the long and short of that. All right, thank you.